This changed something changed.
Oh, yeah, okay.
I think it's the input or something. It switched.
Okay, maybe that. Okay, so that's.
Zoom is always a challenge. I mean, it's just everything was fine the moment the meeting was supposed to start. It switched feed into something, but
it's not you, it's us.
Okay. Oh, all right.
Okay, good morning, everybody. So our first speaker today is Petia Vlahovska from Northwestern, and we'll hear about math and physics of complex interfaces.
Yeah, thank you so much, and thank you for the organizers for the invitation and the opportunity to come to the Fields Institute. It's such a great place, to meet people in math and fluids, Actually, I realized that this is only my second time crossing the border from the US up to Canada. So it's the first time in Toronto. So it's an exciting week. And I will be sharing with you some of the work coming up from my group. So I'm in applied math department at Northwestern, where we do both theoretical and experimental work. So I direct a lab. So actually these videos that you are seeing here are coming from my lab. So we are broadly interested in problems related to nonlinear dynamics in Stokes flows. So these are fluid flows at 0 Reynolds number. So there is no inertia. So they are described by linear equation relating velocity and pressure. So it's a linear PDE. However, evolving boundary conditions can give rise to variety of nonlinear dynamics. So these are some examples coming out from my lab. So this is a droplet of an active fluid. So this is a droplet sandwiched between two plates. So it's like a very fat liquid bridge. And this droplet is activated. So it is filled up with particles that are self-propelled. And so the internal activity, so you cannot actually see the particles because there's gazillion of them. This is a millimeter-sized droplet. So this internal activity gives rise to very strong shape fluctuations and occasionally symmetry breaking, in which case the droplet kind of flies off and moves on. We've worked for a while on electrohydrodynamic instabilities. So this is a video of a droplet in a uniform electric field. This droplet is coated with colloidal particles. So these are a bunch of particles that are just trapped at the interface. And when the field is turned on, there is a flow animated. So there is the electric field generates a shear on the interface, and this shear drives a flow which advects the particles to the equator. So you get this belt of particles. But what it is interesting is that this belt actually goes unstable, and the particles form these counter-rotating vortices. And that instability is yet to be explained. So we've been sitting on it now for, I don't know, 10 years. And so still it's an open question. So in terms of electrohydrodynamics, we also worked with some other instabilities. So this is, for example, a droplet. We're going to look at it from, I want to stop it. So let me explain what we're seeing. So this is a droplet, and we're looking again along the field direction. So this is a droplet in electric field. What the electric field is trying to do is to kind of compress the droplet into a pancake. And what we're going to be seeing is that, the droplet is getting more and more flatter. So its radius is increasing, and eventually it starts shedding rings from the equator. So if we were to see from the side, actually the droplet forms this lens-like shape from which it is emitting, and from the tip of this lens, the rings are being emitted, and then they break up by the capillary instability. Since Axel is here, I wanted also to show a new twist in that instability. So this is a very viscous droplet. Again, we're looking along the field direction, but it's a bit slow movie because it's taken with a very high speed camera with a very high frame rate. So the droplet is expanding, but instead of streaming, instead of forming the rings, what we're going to see is that at some point there will be a dimple formed in the middle, and the interior, the droplet center, it's literally undergoing kind of buckling. There's these wrinkles that start growing and eventually catch up with the rim of the droplet. This is very fresh, literally like a month ago from the lab. Interesting question to look at. So for today's talk, I'm going to focus actually on biological membranes. So in the context of understanding the shapes of cells. So this is an example of an experiment. Okay, this one is not from my lab, from Andreas Bausch's lab, where, where it is? So just to explain, this is a droplet-like structure, but it is enclosed by lipid bilayer membrane. So this is the structures that encapsulate cells. And this vesicle, so-called vesicle, is filled up with active materials, so microtubules and all sorts of gooey stuff that exist inside of cells. And this cell-like structure undergoes these massive deformations. So what you see here, actually, these are microtubules. These are very long rod-like structures inside of the cell. Again, it's active in a sense that it is filled up with stuff called molecular motors. So these are things that are agitating the interior of the cell. So today, after this overview, what I wanted to kind of throw at you is, if you're interested in any of these topics, I'm more than happy to talk to you today and tomorrow if anyone is around. But today I'll talk about membranes. So a bit relation to life sciences. So let me.
All this change of shapes is only because of molecular motors, right?
So for this,
there is no external stimulus.
There is no external stimulus. Yes. Yeah. So this case and this case here, these are internally driven shape deformations. Yes.
Is there a surface tension value?
Yes.
Other physical parameters that still will keep it intact?
Yeah.
And avoid break?
Yeah, so in this case, there is surface tension, and actually the surface tension is fighting the internal activity, the internal stresses. So these shape fluctuations that we saw here, the magnitude of them is controlled by surface tension. So the internal active flow is trying to push on the boundary is pushing back. In the case of the vesicles, I'll work a little bit more. These are more stranger structures. They don't have surface tension. They're controlled by bending rigidity. So I'll hold on to that. Yeah. And actually, the streaming that we saw here, the ring shedding, it's also controlled by surface tension. Actually, the electric field induces charge that actually brings the surface tension to very low values, sufficient to allow for the streaming. Yeah, very good question. So, okay, so let me pause these videos because they have a tendency to freeze my computer. So, okay, so about membranes, just a quick introduction. Why do we care about membranes? So biological membranes are very thin, about 5 nanometer sheet made of, it's a bilayer, so it's of lipid molecules. And these membranes encapsulate cells and cellular organelles, and this, so this is, for example, kind of a cartoon of all sorts of membrane structures inside the cell. So you have the nucleus, the Golgi apparatus, ER, and these membranes, they serve as sort of a trafficking a structure to form vesicles, like a little bags in which all sorts of proteins and important biomolecules are being transported. And so, these membranes also undergo, as a result, they undergo massive deformations. So they undergo something called budding. So it's like a pinching off of a little, droplet-like structure, which is a vesicle. And then these droplets can have to fuse with the target compartment and so on. And so there's been a great interest in the physics community of trying to figure out what is the energy budget for these transformations, so these extreme deformations. And so the classical way to approach the problem is just to kind of consider the static structures and saying, oh, okay, what is the difference between, the undeformed and the deformed state? And the cost of the energy cost is given by the energy, which depends on the curvature squared and also the Gaussian curvature. And there are two moduli, which is the bending rigidity and the Gaussian bending rigidity. If you don't care about topological changes, or if we're just looking for deformations which do not include budding and pinching and anything like that, actually from the Gauss-Bonnet theorem, the term is a constant, so you don't care about it. And so there's been a major focus of estimating and measuring what is this bending rigidity modulus, so that one can estimate the kind of like what energy does the cell need in order to do all these deformation processes involving membranes. So how do we measure? So this is actually a video, highly recommended video from the inner life of a cell, which is kind of illustrating how you get this little vesicle pinching off of the ER. And this is actually a molecular motor walking along the microtubule and carrying the cargo, the vesicle, with its content. And this is the Golgi apparatus, and this is our vesicle. So very soft structures. So you saw this kind of wobbly structure of the membrane, and we'll see that actually the bending rigidity is of the order of the thermal energy. So it's about 10 times the thermal energy. So they're very easily deformed. These membranes are also very fluid. Okay, so since the bending rigidity is so low, these membranes are very easily deformed by thermal forces. And there is a classical phenomenon, which is the so-called flickering. This is a red blood cell under the microscope, and its shape is kind of constantly changing. And the reason is because that it's being kicked by all sorts of molecules which are undergoing thermal motion in the surrounding. And these kicks give rise to thermal fluctuations. And these thermal fluctuations actually have been, they have physiological relevance for interaction of proteins. There is nuclear envelope wrinkling and so on and so forth. But these thermal fluctuations also serve for the purpose of measuring the bending rigidity. So there is methods, there's been a great deal of methods being developed to measure and quantify these thermal fluctuations with the purpose of reporting and measuring the bending rigidity. So today's talk, I will discuss one of the kind of the attempt, like the approaches of how to use thermal fluctuations, this shape flickering of membranes, to deduce and to quantify bending rigidity. So this is not, this flickering or this thermally driven curvature fluctuations of membranes is not a new problem. It goes back almost, like 50 years ago with Brochard-Lennon's work. She developed the first theory for the red blood cell flicker, in which they have considered the membrane as zero thickness, an interface, only controlled by bending rigidity. And there's various modifications of the theory. So Seifert Langer later introduced, they accounted for the bilayer structure of the membrane. So instead of thinking of the membrane as a zero thickness interface, they have considered the fact that you have two monolayers that can slide past each other. And more going on, and and today I will kind of introduce to you our contribution, which kind of focused on the fact that this membrane is actually not only a very thin sheet that resists bending, but it's also fluid. So these molecules are free to flow past each other. And if they are fluid, that means that they have viscosity. And if there is viscosity, that viscosity introduces dissipation. And the question is, how does the dissipation within the membrane impact these fluctuations? So how did I also got into this problem? So this is one of those situations where there is experiments, and there is, people use models to interpret these experiments, but then conclusions are as good as the model used. So, it's a kind of a bit of a cautionary tale that the kind of the path between experimental measurement to a kind of conclusion goes through a model, and one has to be very careful about the model. And so this was a few years ago. There was a paper published that stirred controversy. I'm not going to go into the bio kind of details, but membranes contain cholesterol. It's a molecule that, we think that cholesterol is bad, but actually cholesterol is very important for membranes because it is related to the formation of rafts and so on. And this paper claimed that adding cholesterol to particular lipid, DOPC, stiffens the membrane. So it increases the bending rigidity, which was completely orthogonal to what's been measured and reported in other experiments. So then there was a question, okay, who is right and who is wrong? So, there's been a bunch of people here, Patricia Bassereau and Rumi Dimova, that, say cholesterol does not stiffen the membrane of the OPC. And then there is this new measurement saying that it is stiffening the membrane. So the question is why and what's going on? And so we said, let's take a look at the experiment and what exactly they're measuring and kind of reevaluate the model. So what does the experiment is measuring? So the experiment is something called neutron spin echo. What is neutron spin echo? So it's basically a method in which you, one looks at the membranes. So like this is like a stack of membranes, lipid bilayer membranes. So they're fluctuating because of the thermal noise. So you can shine light or X-rays or neutrons. So like, different energy, rays, and these rays get scattered, and the experiment measures the kind of the scattering. And so in optical microscopy, when we saw the movie of the red blood cell, that's a scattering of visible light, and that scattering occurs on wavelengths, kind of microns. So with optical microscopy, one can visualize thermal fluctuations of things that are big, like vesicles that are 10 microns. The neutrons that were used in that particular experiment, they allow to go down on many length scales to sub-micron and nanometer length scales. And that's why there is a lot of interest in that particular experiment, because it probes the membrane dynamics at the length scales relevant to cells and cellular dynamics. So how does one interpret the data? So in scattering, so what one measures is essentially, so this is, I'm just sketching it here. So imagine you have like a plane, like a membrane. So you take the Monge gauge, you can decompose this interface into Fourier modes. These Fourier modes have fluctuating amplitudes. You take time series of these amplitudes, and the statistics is such that the time correlations have a variance which is directly proportional to the bending rigidity and the wave number, and also they have a relaxation rate which also depends on the bending rigidity and the wave number, but in this case it depends on the viscosity of the surrounding fluid. So relaxation rates are sensitive to dissipation because in order for the bending, for this curvature deformation to relax, it has to displace a fluid, the surrounding fluid. And this flow, well, it has viscous dissipation. So viscous dissipation opposes the elastic relaxation, and that sets the time scale of the problem. So this is in the case of just one membrane. However, in the actual experiment, they're measuring the fluctuations of gazillion of this of membranes. So they're measuring these stacks. And so as a result, and these stacks are kind of randomly oriented relative to the incident ray. And so one has to do kind of averaging to figure out, to take into account the distribution of positive orientation of the stacks relative to the incident rays. So this was done by Granick a while ago, and one gets something called dynamic structure factor or intermediate scattering scattering function. And so it is wave number dependent, and it has a stretched exponential decay, and the relaxation rate is wave number dependent, K. This is kappa, bending rigidity. This is, again, the bulk viscosity, and thermal energy. Gamma is just some constant. So all experiments done with neutron spin echo are analyzed using this approximation, which relies heavily on the assumption that all dissipation is in the bulk fluids and not in the membrane. And we thought, is this a correct assumption? So we decided to revisit this problem about the dissipation and look at the membrane. So just a reminder of what is the mechanics of membranes. So you can describe, the membranes can undergo out of plane deformation, and that energy depends on the curvature, on the departure from the preferred curvature state, the mean curvature, the Gaussian curvature. And then these membranes can also undergo in-plane deformation. So one of them can be area preserving, and the other one is expansion or compression. So membranes actually the lipids tend to be optimally packed. So actually they really don't like to expand or compress. So for all purposes, we can actually treat the membrane as a two-dimensional viscous fluid, incompressible fluid. So this kind of expansion modulus is ginormous. So it really resists compression and expansion. It can undergo shear, and when it undergoes shear, actually this movie shows here. So this is like a little, what they call it, a little raft of cholesterol raft in a sea of lipids, but you see the lipids are kind of moving around a lot. So it's a viscous fluid, and that viscous fluid, if it's an incompressible fluid, has a shear viscosity. There is also another dissipation mechanism in the membrane, which is related to the friction between the two monolayers. So these two monolayers can slide past each other, and there is a friction coefficient associated with that, which is related to the jump, the discontinuity in the velocity of the outer and inner monolayer. And so we said, okay, let's revisit the classical theory and include viscosity. What turns out to be is that actually, if you're dealing with a planar membrane, for a planar membrane, the bending and the shear mode are decoupled. And actually, the shear viscosity of the membrane does not really affect the curvature fluctuations, the height-to-height fluctuations. However, if you are not on a planar membrane, but if you're looking at fluctuations around a non-planar, like for example, spherical, membrane, then actually the bending and shear are coupled. And it turns out that actually in the experiments, in these very controversial experiments, they were doing the experiments not with the planar membranes, but they were doing experiments with the 50 nanometer vesicles. So they were working with very, very highly curved membranes. And what I'm going to demonstrate to you today is that once you start fluctuating around a sphere, then the fluctuations become sensitive to the membrane viscosity at wavelengths comparable to the radius of the curvature of curvature of the membrane. We're not the first one to realize that. So there is actually references here to a few people that have raised this issue that once you have a sphere or a cylinder or anything like that, deformations, curvature deformations are related to viscous dissipation. So, since we're, mathematicians, we are not afraid of equations. But for example, if you look at the kind of like this is like the normal stress balance equation. So if you have a membrane which is curved and it's surrounded by fluids, and you look at, okay, what is the jump of the tractions of the hydrodynamic stresses across the membrane? So these are the hydrodynamic stresses. There is the usual stuff which depends on elasticity, the curvature elasticity. So this is the Helfrich energy tractions, but there is additional actually term in the normal stress that depends on membrane viscosity. So geometry does matter. And so the question is, so now if we analyze the fluctuations, how does it enter? How does the membrane viscosity exactly enter into the fluctuations? So one can do the analysis. So for a vesicle, for a membrane, which is close to a sphere, so we parameterize the surface in terms of spherical harmonics. And then the goal is to derive the evolution equation for the amplitude of these modes. So the modes have a relaxation rate, which is wave number dependent, and then there is some noise due to the thermal fluctuation. So this is kind of linear response theory, nothing singular here. And so what we're expecting to see, so for example, this is what you see under the microscope. So you might wonder, by the way, how is it possible that this is a 50 micron vesicle and the membrane is 5 nanometers? How is it possible to see it? Well, experimentalists are magicians, so they come up with something called phase contrast microscopy, which uses, it's a technique that actually tells you where the membrane is, and then you can, like look at, in this particular case, well, the membrane itself is a sphere, but you're kind of focusing on the equatorial plane, and what you're measuring and what you're observing is the slice. It's the equatorial plane slice. If you want to see how this is in molecular dynamics simulation, so this is actually a movie of this spherical vesicle sliced in the middle, showing what it is doing in real time, fluctuating. This is only 25 nanometers. So, these simulations are extremely computationally expensive. So from equipartition, so like the idea is that whatever deformation is driven by the thermal noise is kind of taken up by elastic energy. In this case, it's bending and maybe some tension. So if the membrane has tension, so incompressibility implies tension. So this is a very well-known result, but the variance basically of the variance of these fluctuating modes is directly related to bending rigidity. And so therefore, by just measuring this flickering by the time series, you find the time series, and then you can find the bending rigidity. So what we wanted to do is to kind of figure out the time correlations and answer the question, are the time correlations, is the relaxation rate sensitive to viscosity? And the answer is yes. It's a bit involved, so I'm more than happy to give you the papers and walk you through the calculations. So there is a lot of fluid dynamics and fluids, membrane interact, like calculating solutions of the Stokes equation around the sphere, and then matching on the interface. And the evolution is basically given by, this is sort of, like the kinematic conditions. So you have some flow driven by this. By the thermal noise, and that, there is a fluid flow, and then there is a relaxation, which is driven by the elastic stresses, bending rigidity, and tension. And so we worked out the calculations. So, and what turns out is that the relaxation rate, so if we look at the relaxation rate, so the relaxation rate, as expected, depends on the ratio of the elastic and viscous stresses. So bending rigidity and bulk viscosity, and this is the radius of the vesicle. But now there is a new term. Here, which is the ratio. So which is the ratio of the 2D shear viscosity to the 3D bulk viscosity. So you can think of it as a ratio of two length scales. So the 2D shear viscosity to the ratio to the bulk viscosity is something called Safman-Delbruck length. And so what this is telling us is that if this Safman-Delbruck length scale is comparable to the radius of the curvature of our membrane, actually our fluctuations are going to be very sensitive to, oh yeah, that works, are going to be very sensitive to membrane viscosity. So Safman-Delbruck, you can also think of it as sort of the limit of, okay, between the flow dominated by dissipation entirely in the membrane versus a flow dominated by dissipation in the box. So it's a crossover length scale. So if you have at very high modes, at very short wavelength fluctuations, actually the effect of the curvature disappears. So the membrane will start behaving as a planar. And of course, your result reduces to the Bouchard-Lennon planar membrane. So you see that there is the viscosity effect enters a quadratic in the wave number as opposed to the cubic related to the bulk viscosity. So there is a crossover wave number beyond which viscosity doesn't matter. So we are seeing that actually our effect is going to be important at kind of long wavelengths. So the wavelengths that are comparable to the size of the vesicle. Is the effect real? Does it matter? So one has to do a little bit of check with the numbers. So let's see what the numbers are. So if you take a typical lipid bilayer, they have very, like, these are PC, they're phosphatidylcholines molecules that are very low 2D viscosity. So this is a nanopascal second meter. So the bulk viscosity is millipascal second. So if you take the ratio of the two, you get that the Safman-Delbruck for this material is about a micron. The effect, so if you're measuring fluctuations of a 10 micron vesicle, you're not going to see the effect. So viscosity, the curvature fluctuations are dominated by dissipation in the bulk. However, if you have either very viscous membrane, so if you can imagine, there is a special, for example, if you have polymers tend to be very viscous. You can also have membranes that are in the so-called liquid ordered state. So I don't know if anyone has done work with liquid crystals, but these membranes, they look a lot like liquid crystals. So they can be either in the liquid disordered state, which is very fluid, so they're kind of, their tails are flopping around, or they can be in a very ordered state. And in that case, the dissipation, the friction between them is higher. And in that case, the parameter goes up, so we should be able to see the effect. And also the effect, even if your membrane viscosity is very low, the effect becomes important for very small vesicles. So you see the radius of the vesicle enters here. So if you have a Safman-Delbruck length scale, which is a micron, that tells you that if you have a vesicle that is 50 nanometer, its fluctuations are going to be pretty much dominated by the membrane viscosity. So this parameter becomes quite large. And so this was our signal that, there might be an issue with these experiments and the interpretation, because their measurements were done with membranes that were having a radius 20 and 50 nanometers. And they're fitting the data with theory, which has no membrane viscosity. So force-fitting the theory with the kind of, inappropriate theory might be problematic. But before we got to their experiment, we said, well, we have to prove that the effect is real. Again, the dogma, the common assumption in the community is that membrane viscosity is very low, so who cares in the dynamics of membrane? But we wanted to demonstrate that it is important, so we decided to do experiments and find a system that is viscous. So these are liquid ordered bilayers, so the DPPC cholesterol. And what you're seeing here, so the actual experiment is, again, remember, this is a three-dimensional sphere fluctuating. We're slicing it at the equator, and we're observing the contour fluctuations in the equator. So you have to go from the 3D spherical harmonic modes to the Fourier modes of the circular contour. This is a standard. It's very easy to map one to the other. And you get the time correlations of the Fourier modes of the circular contour, which depend on the, of course, on the spherical modes. But now, you know, there is contributions. These Fourier modes have contributions from different 3D spherical harmonic modes. So as a result, you end up with autocorrelations that, okay, at very long time, they behave as a single exponential. So all the short wave, all the wave numbers that are smaller than the Fourier mode, they decay, and then basically you're detecting, you're only seeing the 3D spherical harmonic, the mode that corresponds to the particular mode of interest. And at short time, you have it's a bit of a, you know, a power law here, so I'll look at it more carefully. So what we're seeing here is the experiment versus the theory. So the blue line is the experiment. So this is the measurements from actual fluctuations. The red line is the theory with no viscosity, and the black line is the theory with viscosity. Parameter, you know, in that particular case, is 5, so we fitted it. And so you have the single exponential is the solid line, and the dashed line is the complete expression. So what this is showing is that the membrane viscosity effect in this particular system is really not negligible. And you know, again, the long time is exponential, the short time is a bit more involved. So you can actually look at the short times and look at the asymptotics. And we'll see that this also gives us useful information. So if you look at the short times, so it's useful to switch to the 1 minus the autocorrelation function to see how the system is kind of evolving at very short times. So if you have no membrane viscosity, there is an asymptotic behavior which is almost linear. There is a crossover time beyond which, actually, if the viscosity is large, you end up with a power law behavior of the membrane, and then then it goes into the exponential decay. So what we decided to do is kind of actually analyze both the short time and the long time behavior and compare. You know, are we getting, for example, if we're going to fit the data, are we getting, for example, the same viscosity at short times and long times? Ideally, if you know, if everything is perfect, if you have experiments like this one, for example, so these are different modes. So we can measure the autocorrelation functions for mode, let's say 4. I think it's from 4 to 12 or something, 16 or something, 1, 2, 3. Yeah, you get it. So there is a bunch of modes. All of these modes ideally should have the same dependence on the membrane viscosity. That's the only parameter we are fitting in, because the bending rigidity, we can get it from the variance. So that's why we were excited about this experiment, because it allows us to very cleanly separate elastic, the effect of the bending rigidity from the effect of the membrane viscosity. So we can independently get the bending rigidity from the variance. So what's left here in the time correlations is this parameter chi. So and that's where interesting things started appearing. So this is the experimental data. So when we fitted the long time behavior, we started seeing this strange dependence on the wave number. So, we couldn't, within the experimental error, experiments are like this. These numbers are more or less the same order of magnitude. These are the long wavelengths. But then we started seeing this, sharp increase in this viscosity parameter. What is also interesting is that if you fit the data at short times, so one can collapse the data on short times and compare with this power law behavior that was predicted from the theory. And in that particular case, the data collapses. So all the modes, all the data can be fitted with the same parameter of viscosity. So there is something strange going on here. So it looks like at short times, we have a very well-defined membrane viscosity, but at long times, something is kicking in, and it's, that it starts to give deviations. So, I have about 10 minutes left. So I'm not going to go into the nitty-gritty details of what we suspect it's happening. What we suspect is happening is that most likely what's happening is that the bilayer structure starts becoming important. So remember, right now we are treating the membrane just as a zero thickness interface with just shear viscosity. We're ignoring the fact that these bilayers can slide past each other. And what might be happening is that, okay, this is a cartoon. So if the bilayer, if you bend the bilayer, so a very short time, so like you're expanding the outer monolayer and compressing the inner monolayer. And then the lipids are going to start flowing. So the lipids are going to start flowing to compensate this. Now there is a density difference between the inner and the outer monolayer, and that creates the slippage and relaxation. So, and this sort of dissipation due to this sort of bilayer friction, interleaflet friction, is actually important at short wavelengths. And that's what we are seeing. Well, what we were seeing here is that the dissipation seemed to be increasing at the short wavelengths. So I will skip that part here. I will talk about, and I will just conclude. I'd rather have a conversation, if you have many questions about the theory. But I will say that we developed the theory which accounts for the effect of the membrane viscosity on the dynamics of non-planar membranes, and we show that curvature fluctuations around the sphere are sensitive to viscosity. And so now we are actually doing this in silico experiment. So this is a size of a vesicle, which is very similar to the neutron spin echo experiments that were done, the Rio experiment. So we're trying to actually analyze also these fluctuations. And we are looking at kind of two perspectives in terms of quantifying the viscosity. So we can get the viscosity from the fitting of the curvature fluctuations, but you also get viscosity from actually looking at the diffusion of the individual lipids. So you can actually look at the question, okay, what is the diffusion of a lipid, use the Safman, like analogous theory similar to the Safman-Dilbruck for the diffusion in a 2D membrane, and see if we get the same number. And why are we interested in that? Is because there is actually a very, like as we were going through the literature, we discovered that actually the membrane fluidity and membrane viscosity is very, very poorly characterized quantity, and the reported values for its for it are like all over the place. So these are just some examples. So from molecular dynamics simulations, the difference between molecular dynamics and macroscopic experiments is 3 orders of magnitude. And to make things even worse, if you compare with viscosity monolayers, so then there are even another 3-4 orders of magnitude higher. So what is the origin of this discrepancy? We don't know. We suspect that there might be something with the way one goes from kind of a finite thickness membrane to a zero thickness interface, and how do we kind of take this limit properly? So stay tuned on this issue. And I would just mention is that, okay, I motivated the experiment, the theory with the experiment with the neutron spin echo, and again, sorry, I didn't have time to go through it, but I would just say that this is the experimental data. This is the new theory with viscosity, and this is force fitting, literally force fitting the data with the old theory. And if you force fit it with the old theory, it's just it's a by pure fluke you get a value of the bending rigidity which makes sense, but it is totally off. So it just happened to be okay for that, you know, like it's the right order of magnitude, but it's just not it's just not right to force fit. So thank you so much for your attention. I'll be happy to answer questions.